Hello and welcome back to Let's Code Physics. This is the first episode in a new series where we're going to be simulating the motion of stars and planets under the influence of each other's gravity. I am wearing my sunglasses for the beginning of this episode because my nephew Carter asked if he could be on my YouTube channel. And the only way I know to make it a YouTube channel is to wear sunglasses. So Carter, there you go. You are now on my YouTube channel. We are going to be starting this gravity code with the Bouncy Ball code that we just finished last week, our subscriber tribute. The reason is I've got all this great structure set up already in that code to keep track of multiple objects. And so there's no sense in reinventing the wheel, so I'm just going to turn those bouncy balls into planets. My goals for the episode to help me remember are these over here, just so that way I make sure to remove everything I need from the scenario there. So what we're going to be looking at is the motion of multiple objects. I want to be able to change the number of objects. That's why we're going to be using the list environment again, under the influence of a gravitational force. We'll get into a little bit more of the details at first, but first I need to go through all my little housekeeping items here to make sure that my code gets set up appropriately to handle objects in space and not bouncy balls in a box. So we're starting with the 3D bouncy ball code so that I don't have to set up all the list information again. The first thing we're going to do is we're going to get rid of all of the walls. Now I've gone ahead and saved this under a different file name, so that's good. So we're going to go ahead and get rid of everything having to do with creating the box because there's no boxes around these planets in space. That might be an interesting thing to add back on at some point. Let's see. So we're going to remove the walls and the wall bouncing conditions. So I'm not going to go in order of the code. I'm going to go in order of I'm going to do like one concept at a time. So let's see. So I want to get rid of all of this business of checking whether the bouncy ball is bouncing against the wall. So there we go, right? So now there's no more boundary, no more bouncing off the boundary, so that's good. I need to remove the pressure and temperature calculations. So let's get rid of... Actually, I tell you what, I kind of want to keep these graphs for later. So what I'm going to do is I'm going to comment them out, and we'll change the names of these a little bit later because we will want to graph something. Create graphs for things. There we go. And I'm going to put a little double hash mark there just to remind myself to come back to that later. Let's see. So instead of a bouncy ball animation, we are going to call that planetary. Actually, yeah, planetary motion. That ought to be fine. Okay. Let's see. So I need to remove everything having to do with the pressure and the temperature. Let's see. That is, I don't think that gets set up. Yeah, that gets set up down here. So let's get rid of that. It isn't that, that calculating those things would be bad. It's just that, there's no real meaning to pressure of the planets in space. I suppose we could keep this as like a calculation of the total kinetic energy, but actually what we're going to be interested in is the total energy, kinetic plus potential energy. So we'll get to that in a little bit. Probably the next episode we'll get into the total energy calculation. Let's see, so temperature, pressure, average pressure, and then the graphing, double hash mark to remind myself to come back to that, just because, so that way I don't have to go and take a little intermission with the elevator music to look up how to create a graph in VPython. There we go. Let's see. So we've got remove the walls and the bouncing condition, remove the pressure temperature calculation check, remove the recent collision check. So you remember before we were doing this check for whether two bouncy balls have recently collided. We don't want to do that anymore. In fact, we want to go ahead and get rid of everything having to do with the bouncing, because now instead of having no interaction, no interaction, no interaction, sudden interaction, no interaction, no interaction, no interaction, the objects are going to be interacting the entire time. You can't escape gravity's interaction. It just becomes very, very weak. So we're going to get rid of all of this having to do with the recent collision. And in fact, let's go ahead and I tell you what, let's keep this let's keep all the index and r hat stuff. That might be useful later, but all of this exchanging of velocities and momenta and things, that's not going to be happening anymore. So we'll get rid of those. There we go. Oh, there's a kinetic energy calculation. I missed that one. Let's see. Yeah, so we'll still have that update. We'll need to change that in a little bit. So what I'm going to need to do here is I'm going to need to make a note to myself, add gravity force here. I need to reduce the number of bouncy balls to 2. So what I'm going to start out with is I'm going to start out with the Earth and the Sun. So we know the values for the Earth and the Sun. We did that in a previous episode. I'll link to that in the description below for how we got those. But we're just going to check out the Earth and the Sun because we know that combination works because we have not fallen into the Sun's fiery depths. So we are going to get rid of all but 2 of these. Yeah, let's not that it matters. We'll delete. Oops. Yeah, we'll delete these. Then we'll delete the names. So it's not like we're just keeping United States and United Kingdom. There we go. Let's have this be the Earth and this be the Sun. There we go. And we'll leave these blank for just a second. So actually I don't need to change the number of bouncy balls calculation because this is just the length of the list -1. So that'll be 2. Cool. Let's see here. Delete. So now all these, it's going to seem like a little bit more powerful machinery than we need with all these, with all these counters and everything because we just have 2, but soon we'll add in a 3rd one, maybe even a 4th one, and then we'll want to have that machinery set up. Okay. Let's see. Reduce the number of bouncy balls to 1 planet, 1 the sun. So so number 1 is going to be the sun. Number 2 is going to be the Earth. Okay, so that is IVB equal 1, and this is IVB equal 2. Just to remind myself. Oops. Well, that's weird how that backspace took out all the spaces. Okay. Okay. So let's see. So we started with the 3D bouncy ball code check. We removed the walls and the wall bouncing condition, removed the pressure and temperature calculations. We removed the recent collisions check, and we reduced the number of bouncy balls to 2. 1 for the Earth, 1 for the Sun. In fact, I know this is the outline I'm using now, but there we go. Earth. There we go. Let's see. 1 Earth. Yes, we have 1 Earth. Last time I counted, we had 1 Earth. Now we're going to change all of the information. So we had all these, masses that were dependent on the number of subscribers in the country, these randomized initial conditions, not so anymore. Now we're going to use the Earth mass and the Earth radius. So let's start with the Earth mass. We'll put that in here, paste. Same thing, we'll put in, well, I guess I better go down the list. Now let's do it all one. Let's do like properties at a time. So we're going to take the sun mass, copy, and paste. Cool. There's the sun and there's the Earth. We are 6 orders of magnitude different. So that is 1,000,000 times more massive. Well, not quite 1,000,000. This one's a 6. This one's a 2. So something like 1,000,000 times more massive the sun is than the Earth. Let's see. So we've got the bouncy ball list that'll contain the planets. So maybe at the end I'll do a massive replace of all the instances of BB to. Actually, no, I don't want to say planet because one of them's a star, and in fact, in a little bit we're going to do a binary star system. So we'll just keep the name the same, yeah, until I come up with something better. Let's see. So this section here to initialize everything was initially set up as a counter. I don't really want it to be a counter anymore because I don't want these things to be randomized. So we're going to untab all of these. So actually, there's an easy way to do that under. Well, it's easy if you don't get rid of your selection there. All right, so there's an easy way to do this under Format, Dendent Region. Cool. And I can get rid of this thing and my attempts from last time of making a trail visible. Save. Let's see here. How do I want to set this up? I want to start out with just a 0 at the beginning, just so that way it starts out the list. And then we're going to, let's put in a comment, set up body 1. In that case, this is the sun. IBB equals 1. There we go. And we can get rid of these. Okay. Why don't we call these things X, Y, and Z, so that way I can set the numbers separately in one block and then put them into the thing in the other block. So let's have, let's see, so this is the sun. So the sun's initial position is going to be 0, 0, 0. It's pretty much going to stay there. The sun will move a little bit. We do make the sun wobble ever so slightly. Well, Jupiter makes it wobble more than we do. But we do make the sun wobble ever so slightly. But it's not going to be terribly visible. But anyway, the sun is going to be at the origin there. Okay, and then I need the sun's radius. So why don't we call that rad? So let's see. So the sun's radius is this much, 696 million meters. And so again, this is just, I'm going to put the numbers up here, and then I'm going to put the variables names in here, just so that way I don't have to, you know, look for the specific line where it had a specific number. Rad, cool. Let's delete that comment there. We know what that does. So the position is going to be this. Color, let's make it a beautiful yellow. Although I suppose in keeping with that, I should put the value out here. Why not? Color equals call, make trail equals, and we'll just make that true. Okay, so I have a closed parentheses for the sphere and a closed parentheses for the list append. And that closed parentheses gives me the little jingle noise. Okay, cool. All right, so I've given the sun. So I've made the sun. I've created the sun. Sorry. So I've created the sphere that represents the sun, and now I have to give it its velocity. So let's call that maybe Vx, a Vy, and a Vz. Go. And so we're going to put the sun initially at rest. I might not have put that in my notes, but it's kind of implicit that we're not going to have the sun shooting around the place, at least not at the beginning. Might do that in a little bit for fun. So the velocity list now gets this thing. Okay, cool. So we have now taken care of all of that about the sun. We've put in the sun's mass, and we've set up its body there representing it. Save. And we're going to copy. Oops. Well, it looked like my cursor was down there. Okay. Now we're going to do the same thing for body number 2. So this is going to be the Earth. This is where we've got to be a little bit more careful with it, because we want to set up the Earth with an accurate depiction of both its distance from the sun and its velocity around the sun, because if we don't give it enough of either, it will end up in the sun, and we don't want that, right? Let's see. So we're going to give the Earth a position of its perihelion. We got this value a few episodes ago in our route finder in space, and so that's just going to be the x-coordinate. The rest is going to be 0, so it's going to start out in the x direction there. And then I need to give it its radius. The radius of the Earth is significantly smaller than that of the sun. Now I'm going to put these values in for now, but I'll probably end up multiplying them by some number to make them visible. I tested this out a little bit earlier, and they end up being very tiny dots because we are very tiny compared to our distance from the sun. And actually, I'm going to get rid of this. I'm going to show you something cool in just a second. You've probably already spied it over here. Let's see. So we're going to be adding this. So sphere is equal to the radius, position to XYZ. Yeah, you see we are 6 million meters in radius, but we are 147 billion miles from the sun at perihelion. So yeah, we're not going to be terribly visible on the simulation at first. I did find a cool thing. Actually, one of my students pointed this out, that you can go with texture equals textures.earth, and it's going to make it look like the Earth. It's going to give it the surface of the Earth. It's really cool. Okay, so the initial velocity of the Earth, of course I didn't give myself a number. I made myself have to calculate it. Okay, so in order to get the velocity of the Earth, it's difficult to get that because we need the velocity at a particular point. The velocity of the Earth changes ever so slightly as it goes around the sun. We saw that in more extreme values. You saw the more extreme values in the animation in Route Finder in Space Episode 1, where, for example, Halley's Comet, not Halley's Comet, but Halley's Comet. I think that's how you say it, because I said it Halley last time and I got corrected. Well, the comet, the comet everybody knows about, it's got this dramatic change in speed as it goes around. We don't have such a dramatic change in speed, but we do need to get the instantaneous speed there. But it's difficult to get the instantaneous speed, but it's really easy to get the average speed. So here's how you can convert one into the other, is by using the wonderfulness of conservation of angular momentum. Take 2, the wonder of conservation of angular momentum. So we're going to calculate the Earth's angular momentum as our average distance from the sun. So that is 1 AU, which I did not record in my notes. So I'm going to look that up. And we're going to multiply that by 2 pi. 3.14159. That ought to be good enough, right? Times our average distance from the sun again. So I may as well square that, I suppose. Times our mass. So we're going to say mass list. Actually, I can cancel that because no, let's go ahead and calculate it. Mass list of 2, because that's where we are. We're on body number 2. Divided by, now we need the amount of time it takes for us to go around the Earth. So this is our distance from the sun, our average, not our average, our distance that we travel around the sun. This is our mass to give us, this and this piece give us angular momentum, and then we're dividing by the amount of time it takes us to go around the sun. So that is 360. Dang it, numlock, can't you just stay on for once? So, excuse me, take 2. We're going to divide that by the amount of time it takes us to go around the sun, which is 365.25 days, times the number of hours in a day, times the number of seconds in an hour. We're going to close that up. Cool. And so our velocity, we can't have a velocity in the x direction because we're going to be going around the sun. So we're going to have a velocity in the y direction. So that's going to be our angular momentum divided by our current distance from the sun, so our perihelion. So you notice in the angular momentum calculation went the average distance. So I suppose I could make that more comparable by making that times 10 to the 9. Here we go. So in here's going our average distance, but in here's going our current distance from the sun. Since this was the average time over here, we need the average distance over here. So we're dividing by the Earth's distance from the sun times our mass. Is why I probably could have done without the mass, but you know what? I might need angular momentum later. So there we go. There we go. So we've got angular momentum there. Cool. And yes, I have added the Earth texture. Thank you for reminding me, Word document. Okay, cool. So we're adding the Earth to the list here. We're adding the we're adding the velocity of the Earth to the list there. Okay, cool. So we've got our radii in. Let's just double check here. Earth mass, Earth radius, Earth position, Earth angular momentum, velocity, texture, sun mass, sun position, radius. Okay, cool. So what I need to do next is I need to go down here and actually replace this with the gravitational force. Or put in the gravitational force here. So the gravitational force involves this distance between the two bodies, and so that's a useful thing that we'll need. The way the gravitational force works is that we need to calculate a gravitational constant, capital G. So we're going to define that up here. And that thing is 6.67 times 10 to the negative 11. It is a teeny tiny number. So this is our gravitational constant. Times the two masses. So times mass list of IBB. Oops, I need a square bracket there. IBB times mass list of IBB2. So it's the product of the masses divided by the square of the distance between them. Okay, so if you double the distance between two objects, you cut the gravitational force by a quarter, or into a quarter, by 3/4, down to 25%. There we go. And then the thing needs a direction because this is a force, so I need to multiply the whole thing by the r hat that we already had there. Isn't that great? Okay, and this is going from IBB2 to IBB1, and let's see, is that the way? So this is going to be the force on IBB. So IBB needs to be the one at the... No, this actually needs to be flipped. Yeah. So this is going to be the force on IBB. Here we're going to calculate excuse me. So here we're going to calculate force on IBB. And what I want to be able to do here is I want to be able to have multiple bodies at work here beyond just two. So what I'm going to do is I'm going to say that this is the force list on IBB. And I'm going to say that that's equal to force list on IBB plus this thing. So this thing is going to start out at 0. So all of the forces are going to start out at 0. So force of IBB equals 0. Cool. Now, and then what I can do is I can, when I have multiple objects going on in here, this second counter, this IBB2, looping over all the ones that aren't IBB, is just going to keep adding to that. Now, here's the thing is that I've got this wonderful calculation saver because I don't want to double count the forces, because the force of IBB on IBB2 is the negative of the force of IBB2 on IBB. So if I've calculated one, I've calculated the other. There's no point in calculating them over and over again. So actually, I'm going to take this part out of here. I'm going to initialize. Here's what I'm going to do is I'm going to initialize them all to 0. Well, IBB is less than or equal to NBBS. What I'm going to do is I'm going to say force list of IBB. And I do actually need to create this array earlier, so I need to remember to do that. I'm sure it will remind me when I forget. So what I'm going to do is I'm going to set them all equal to 0. And then when I go through this loop, I'm going to be simply adding the forces together. And what I can do is I can say that the force list of IBB2 is going to be modified by the thing that I just calculated, only by the negative, minus force list of IBB. So what this is doing is it's saying you've already calculated this vector, you've already calculated this quantity, so there's no point in recalculating it, right? Because this thing is, it's several operations. This is going to cut the computational time down because it's already got that number stored. The negative just means that the force of one on the other is the negative of the force of the second one on the first one. Cool. And then, of course, we need to be incrementing IBB2. Again, this is a little bit more complicated than we really need for just the Earth and the Sun. But when we have 3, maybe 4, maybe a bunch of planets running around, this is going to be important because we don't want to have to manually add in a bunch of calculations. Okay, so I created this list. I need to actually set it up. Let's see here. Let's initialize that down here. So let's do force list equals just a 0, and then we'll do same kind of loop that we've had before. Oops. Less than or equal to. That loop would not have gone on for very long. While IBB is less than or equal to number of bouncy balls, force underscore list dot append vector. And this is actually a vector, right? Force is a vector. Okay, cool. So we've got our force list appended, not appended. I'm getting hungry. All right. All right, so let's see here. So I've created the force, but the force isn't doing anything yet because I've just got the position being updated here. So what I need to do now is I need to update the velocity. Excuse me. Okay, cut back. In order to update the velocity, I've got to take the velocity list of IBB. Just needs to equal the old velocity plus, so the way velocity gets modified is by acceleration times dt. Acceleration is the force divided by the mass. So we've got force list of IBB divided by mass list of IBB times dt. Cool. So we've got, I don't think I need this thing anymore. So now I can actually, I can see it now. It's wonderful. Y'all have probably been yelling at me for the last 5 minutes. Can you please maximize the code window? We don't need your to-do list anymore. So I've got new velocity equals old velocity plus force over mass times dt. New position equals old position plus velocity times dt. Okay, cool. And update body IBB velocity. I'll go back through after this and change all the bouncy balls to bodies. There we go. Okay, cool. And that's all taking place in the IBB loop. I don't need this reminder anymore. Thank you. Okay, so let's just give this another once over before we run it. We have our masses. We've got the sun and the earth. We've got our lists initialized. We've got the sun here at 0, 0, 0, not moving initially. And we've got our earth here at this far out in the x direction, traveling at this fast in the y direction. These are in parentheses, so they're both in the denominator. That's good. Let's see. So we've got this thing being added as a vector. We've got our force list being appended here. I suppose it doesn't matter that that's a vector right now, but you know, it wouldn't hurt. Actually, I do want that because I want to start out at 0, although it's putting it at 0 right here. Oh, actually, I need to make this not into a scalar, but a vector. There we go. 0, 0, 0. Let's see here. So I've got the loop starting here. I've got the next loop starting here. So with this starting out at IBB plus 1, no planet is going to interact with itself. We're taking the difference between these two. We're taking Armag. We're taking... I guess I didn't really need this, but we might use it later. I'll comment it out for now. Just be consistent with my... Actually, no, let's put it out front. There we go. So I've got my R hat here. I've got my calculating the force on IBB. So this is force equals G times... Actually, I went to all that trouble of setting that up, and now I need to put that as a negative, so that way it's pointing inward. So here's a way to think about this. If IBB is the Earth and IBB1 is the sun, then when this is 0 for the sun, this is just going to be where the Earth is. And so R hat is going to be pointing out toward the Earth. That negative means it's going to point back in toward the Earth. And then this negative means it's going to be pointing back to the Earth. Sound good? Let's see here. So we've got G M1 M2 over R squared R hat. That was the gravitational force last time I checked, meaning last time I taught it in my class. Force list equals force list minus force list. Okay, cool. This is 2, 2, and 1. Or no label. I'm not making that mistake again. Just kidding. I can't guarantee that. So we've got our velocity list here. Okay, we should be good to go. Let's give this thing a go. Let's hit F5. See what we get. Uh-oh. Textures is not defined. Okay, so I tried to do something fancy. Let me look that up. VPython textures. Oh, it's not textures, it's materials. Pardon me. Material. I don't know. Why did I think it was texture? I don't know. Okay, so let's go up here. So I tried to show you something cool, and then material. Materials. At 5. Oh, oops, I gave this thing rounded parentheses. Oh, fortunately I called everything by list. So let's search for any instance of list with a rounded paren, like down here. There we go. All right. Try this yet again. Come on, just give it to me. Just let me have this. It hasn't thrown an error yet. All right, let's keep that one over there for right now. Let's see, I did put in a rate statement, didn't I? Yeah, rate 5,000 might be a little fast. Actually, no, that's probably going to be just about right. Oh, and actually our DT, so this is now in seconds. We don't need that many seconds between steps when dealing with the Earth going around the sun. Though I doubt that's the issue. All right, I tell you what, let's put in a print statement here, entering loop, save, and let's see, so we're doing T there, DT equals 10. Oh, memory error. Oh my, line 59. Saying I'm using up too much memory at line 59. So we're going to look for line 59. Oh, whoops, I forgot to put in the IBB counter, which I would have discovered in just a second when I didn't get that print statement out. All right. I just, I love my code so much that, I just want them to run over and over and over again. Oops, I did call something IBB1. Oops. Oh, whoops, that should be 2. Yeah, because it's the Earth's minus the Sun's. Or, yeah, that's the way I'm going to think of it, yeah. No other IBB1s. All right, try it again. Oh, okay, cool. So this is working, and I told you that they wouldn't be very visible. This little yellow dot is the sun. The little yellow one is the sun. And then this one that looks like the Earth, right, is the Earth. Now, I did mention that these things were going to be really, really small because when you take these things to scale of this being the distance from the sun to the Earth, this is how tiny we are, is that we're at the tip of this little trail here, and this is how small the sun is. So this is our distance from the sun compared to the size of the sun and the size of the Earth. So I'm going to change 2 things. Number one, I'm going to make this thing move faster because this video has probably gone on long enough. So we're going to change that from a 10 to 100. So it's going to be going in order of 100 seconds. I think that's okay when one loop takes a year. I'm just going to guess that. And then I'm also going to take their radii and multiply them by, let's see, I don't want to make them too much bigger. Maybe by a factor of, say, 10. If they end up engulfing the screen, then I know I can cut them down. So let's try that. Okay, cool. So the sun is much more visible. The Earth is still really, really tiny. You can't see the Earth texture on it. We're going to zoom out here. So we've put in the values for the Earth and the sun. So this should end up being a nice, complete circuit around the sun in almost a circle. Remember, we're about 3% off from being a circle. That number is not meant to be something technical. And it looks like we're going to be all right. As this thing should be symmetric going around, but we'll sit and watch a complete cycle just to be sure. So to give you an idea of what else is going to come up in this series, we're confirming here that the code works by watching the motion of the Earth and the sun. And then what we're going to do is we're going to look at a little more interesting scenario. So what we're going to do is we're going to replace the Earth with another star, and we're going to look at the motion of 2 bodies of equal or roughly equal masses around each other. That's going to be pretty cool. And then we're going to take a look at what happens when we add in multiple bodies. So we're going to try, multiple body systems where it's not just, okay, they're going around each other in ellipses. That's wonderful. We'll get, some more interesting stuff looking at there. Okay, so the Earth has made a successful trip around the sun, and I promised you that this thing would look like the Earth. So what I'm going to do is I'm going to tilt the orbit toward us. I can just barely tell that it's headed toward this part of the screen. We're going to zoom in toward that make trail, and I think the Earth just flew by. I'm not sure. Where are you, Earth? Oh, I lost the Earth. Tell you what, just to prove to you that it does look like the Earth and that I'm not crazy with this thing, let's increase the Earth's radius by another factor of 10. No, still not enough. All right, then let's go with a couple extra zeros, right? Okay, so there goes the Earth around the sun. I probably didn't need that other 0, but this does show you that it does end up looking like the Earth when you put in that materials property. So that's actually pretty cool. It's even better if you rotate it. Yep, there we go. There's the sun over there. So we're not going to gonna make the sun any larger, or else we might get engulfed by the flames. But anyway, I leave you with this wonderful distorted image of the Earth going around the sun. Here we go. We'll put it like this, and that way it looks like it's just perspective, from the International Space Station or something. So from this amazing view of outer space, I wish you all the best, and I thank you for watching, and I'll see you next time. Bye-bye.